right, this section is deals with bond energies and bond enthalpies. Remember that one of the things that we learned about when we looked at potential energy diagrams is that many times we look at the reaction. Here is the enthalpy of the reactants, here's the activation energy, and then here is the exothermic. So this part is the endothermic process, this is the exothermic process. And here we can see if it's exothermic, we can see that the enthalpy of the products is lower than the enthalpy of the reactants. Now if it's endothermic, let's think about it the same way. If this is enthalpy over here, just like here, in the past we oftentimes said that was energy. Well, now we can be a little bit more specific now that we've learned about enthalpy. in an endothermic process, might start like this and then go like that, where again this is the enthalpy of the reactants, this is the enthalpy of the products. So in an endothermic process we can see that the enthalpy of the products is greater than the enthalpy of the reactants. And again, like I just said, in an exothermic process, in an energy releasing process, the enthalpy of the products is lower than, that's our products there, the enthalpy of the products is lower than the enthalpy of the reactants. Okay, and what that leads to, it leads to this idea of bond energies. Okay, and the bond energy really is a measure using enthalpy of how much energy it takes to break bonds. Remember, that's our breaking bond point right there. How much energy it takes to break the bonds, and then also how much energy is released when these new bonds are formed. So again, there's our exothermic process. Whoa, that's our exothermic process right there. Okay, and so bond energy is just that. It's just how much energy are in those bonds. Does it take to break those bonds for that, again, that climb up the hill, and then how much energy is released when those new bonds are formed, and that, again, is our energy releasing process. So we know that in a bond that atoms are attracted to one another. Okay, when the outer electrons of one atom, they're electrostatically attracted to the nuclei of another atom. And again, the attraction between those two atoms makes them increasingly stable, giving them lower and lower potential energies. Okay, as the atoms continue to approach one another, so imagine you've got two hydrogen atoms that are far apart, and they start getting closer and closer together. Okay, so imagine that. So as the atoms continue to approach one another and get increasingly close, there comes a point where the two nuclei, so you've got your protons there in the middle, and also the electrons on the outside, they're going to start to repel one another. We know that there's an attraction between the electrons of one atom and the nucleus of another atom, and vice versa, between the other atom and the other nuclei. Okay, but we also know that electrons repel each other, and so do protons. So as they start to repel each other, the potential energy is raised and the two atoms become less stable. Okay, what happens is you get this happy medium is reached, and that's when the bond is formed, where you're at a distance where the attraction is still as great as possible, but also the repulsion is the lowest as possible. Okay, and the distance is called the bond length. So whatever distance it ends up being, that is the length of the bond. Okay, and the potential energy at that point is what we consider to be the bond strength. So again, this over here is the bond strength, where up here, this number is what we call the bond length. Okay, so a typical plot for the formation of the simplest molecule, hydrogen, is shown below, where the bond length is about 74 picometers and the bond strength is about 436 kilojoules. Okay, now something to think about here is, what if we, again, just like what we always do, you know, when we're doing like those Maxwell-Boltzmann drawings where it's, you know, like these, and we have the activation energy there. This is the low temperature. This is the high temperature. Same thing. What if we did another atom on here, something like, let's compare like oxygen. Okay, if we put oxygen on there, Oxygen, we know, has a double bond. Okay, and a double bond is typically stronger than a single bond is. We know that H2 is a single bond, whereas oxygen with a double bond is going to have a stronger bond strength. So that's something that we need to consider. So in terms of internuclear distance, you might think, well, a double bond is shorter, but then at the same time, the oxygen atoms are bigger. So in terms of bond length, I can't really predict off the top of my head whether the oxygen bond length is going to be bigger or shorter than hydrogen's is. I'm guessing it's probably going to be longer just because hydrogen, it's so small. But again, I'm not going to make a prediction about that. Okay, but what I do know is that because oxygen is a double bond, that its bond strength is going to be much, much bigger. So let's just assume they have the same internuclear distance. Their bond length is the same. Okay, if I were to assume that, what would the oxygen curve look like? It would look something like this, where it would go down farther and then come back out. Okay, and so really you would go, oh, this one here, if there's two drawings on there, you would assume that that is oxygen because oxygen has a double bond where hydrogen only has a single bond. And in terms of internuclear distance, again, we could probably guess that oxygen's peak is going to be probably over here. But again, really the big difference between H2 and O2 is, again, you've got an HH single bond, where in oxygen you've got an oxygen-oxygen double bond. Okay? So when you're if they give you a graph, and I'm thinking of your tests coming up, when they give you a graph of different ones on there, that's really what you're looking at, is you're looking at, okay, is there really a difference in their bond length? Usually it's the bond strength that will give away which one it is. But sometimes, again, like oxygen, you could probably assume that oxygen's going to have a bigger internuclear distance. Okay, but if you compared, for example, like fluorine and oxygen, which is also a single bond, you might look at the periodic table and go, okay, well, fluorine atoms are smaller than oxygen atoms, but oxygen has a double bond, so I don't know which one's going to be smaller. Well, you're exactly right. You don't know which one's going to be smaller in terms of bond length, but again, because oxygen has that double bond, its peak down there is definitely going to be lower. Okay, so that's what you need to know about these types of diagrams. If you see a diagram like this, that's really what you need to know, is that usually it's bond strength that differentiates them. But again, if it's very obvious, like hydrogen versus oxygen, then yes, you will notice a difference in their bond length as well. Okay, but a single bond is not going to go as far down. A double bond is going to go farther, and a triple bond, something like N2 would even go farther down. Okay, since the forces of attraction that stabilize the atoms when they bond are attractions between electrons and nuclei, the greater the number of electrons involved, the stronger the attraction. Again, what we just talked about. Basically, they're saying that's the double bond there. Okay, and as such, triple bonds tend to be stronger than double bonds. So again, here we can see that double bonds stronger than single bonds, and then shorter bonds also tend to be stronger than longer ones. Okay, I think we covered that one well enough here. Okay, so here's an example of this where we've got three different elements, diatomic molecules, it says. We've got X2, Y2, and Z2. Okay, now it says, based on the data in the graph, which of the following correctly identifies the diatomic molecules X2, Y2, and Z2? So X2, as we can see, is not only a weaker bond, but it's also a shorter bond. So internuclear distance-wise, this one's much shorter than the other two. So if I'm going to choose, and you'll notice that all three of them have hydrogen, nitrogen, and oxygen in them. Okay, if I have to choose between those three, which one's going to have the shortest internuclear distance? I'm definitely going to choose hydrogen. Okay, I think that X2 is certainly going to be hydrogen, simply based on the fact that it has the shortest internuclear distance. Okay, but then between N2 and O2, again, we have that same question of, well, oxygen atoms are smaller than nitrogen atoms, so they're going to be closer, but nitrogen has a triple bond, oxygen only has a double bond, so internuclear distance-wise, they're real similar, and so we don't necessarily know, exactly which one is going to have the smaller internuclear distance. But we do know that Y2, this one, goes way farther down, so again, we can identify that as being probably the triple bond of N2, when this one is just the double bond of O2. So therefore, Y2 would be nitrogen, and then Z2 would be oxygen, so the correct answer is A. Okay, now let's take that a little bit further there, and let's talk about bond strength. Okay, the strength of the bond in a diatomic molecule is what we call the bond dissociation energy. It's how much energy it takes to break the bond. Okay, so for H2 to become 2 hydrogen atoms, to break that single bond between the hydrogen atoms, it takes 436 kilojoules of energy to do that. Okay, now let's consider a polyatomic molecule such as methane. Okay, methane has 4 identical carbon-hydrogen bonds. We know that that is sp3 hybridized, so every single bond is equal in its energy, but they each have a different bond dissociation energy. Okay, and what that means is as you take a hydrogen away, those other hydrogens initially are a little bit more attracted. So you take one hydrogen away and it takes 440 kilojoules of energy to do that. You take the second one away and it takes 460 kilojoules. Okay, and then it starts to go back down. And really what you need to know about this is that every molecule is going to have not every single atom is going to take the same amount of energy to break that bond. Okay, the individual bond association energies vary since in each subsequent bond breaking, the environment in which the reaction is carried out is slightly different. And this has the effect of making the strength of each individual bond also slightly different. Okay, so in order to overcome this, well, wait a minute, so how do I know which bond am I taking away? If I break all 4 of those bonds, do I have to add up all 4 of those? So in order to overcome this complexity, we may define the bond energy as an average of each of the 4 separate carbon-hydrogen bonds. Okay, now here's the key. We've learned one way to calculate the enthalpy change for a reaction is to take the Q value and divide by the moles. Okay, that's something that we have already learned. You can use Q equals MC delta T to get the Q value. You can then take that value and you can divide by the moles, and that gives you the delta H. If delta H is positive, we know it's endothermic. If delta H is negative, we know it's exothermic. Okay, another way to calculate the enthalpy change has to do with this, because in order to break a bond, energy must be put in. Okay, it takes energy to break a bond, always. Okay, it's an endothermic process. Delta H is positive always. When you create a bond or you make a bond, again, 100% of the time, energy is released. This is an exothermic process and has a negative energy. Okay, and when we think about that, well, wait a minute, can't we just take how much energy it takes to break the bonds and how much energy it releases, and we can determine the enthalpy change from that? Absolutely, yes, we can. Okay, so another way to calculate the enthalpy change is we can say that delta H is equal to the energy of the bonds broken. And again, what bonds are broken? The ones in the reactants. And then I'm going to put a minus in here, and I'm going to explain why here in just a second. Minus the energy of the bonds that are formed, which again, where are bonds formed? In the products. At the beginning today, I had drawn those energy diagrams again with enthalpies here on the side. And remember that that first part, however big that hill is, let's draw it again so we can see a little bit better. Okay, remember that this part right here coming up to the top, That's the endothermic process. That's the part that requires energy. That's where delta H, again, is always positive. But then once we reach the part where we're in that transition state, where we have that activated complex, where we're between the reactants and the products, now this is always an exothermic process where delta H is negative. So coming back to the equation that we just drew involving bond energy, and I said that the enthalpy change of the reactants, the energy of the bonds broken minus the energy of the bonds formed. Why is that minus in there? Because remember, this part right here is the part where energy is released. So this is our positive component, and with that negative in there, that now makes that our negative component. So when we put those two together, then we know that that's overall is going to give us the enthalpy change for the reaction. Okay, so let's come down here now. The energy change in a reaction is calculated by first summing, so adding up the energy required to break each of the bonds, which is a positive value. Again, that's this component right here. Then adding up, summing the energy released when making each of the bonds in the products, which again is a negative value. Okay, and then you add the two together. So wait, does that mean you should put plus and then put a minus here? Sure, you can say plus and then put a minus there. It's the same thing as subtracting. I don't really care how you do it. Okay, but that absolutely is a great way to calculate the enthalpy change, is taking the energy of the bonds that are broken and then subtracting the energy of the bonds that are formed. Okay, now if the total energy needed to break the bonds is greater, so again, if breaking the bonds is greater than the released, then of course it's endothermic. Okay, and of course we know that the temperature overall is going to go down of the surroundings because it's absorbing energy from the system. Okay, if the total energy needed to break the bonds is less than the energy released, then of course it's exothermic. And then of course it's going to feel hot because heat is exiting the system. Okay, and so here we have an example of this. It says, using the bond energy table on the left, answer the following questions. So it says, calculate the standard enthalpy of the reaction below. So what we need to do is we need to take our, basically we need to draw out our molecule here and then count up the bonds that are broken. So that's our first molecule, and then we're going to plus HH, and it's going to make CH3, CH2, CH3. So overall, on our reactant side, let's first of all focus on the bonds that are breaking. Okay, so let's figure that amount out. So I count 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So then I come over here to the side. Carbon-hydrogen bond is 412. So I'm going to go 6 times 412. Okay, so that takes care of those bonds. 1, 2, 3, 4, 5, 6. And then I count a carbon-carbon single bond right there. So then again, I come back to here. It looks like that one is 348. And then here's a carbon-carbon double bond, which is 612 from right here. And then we have a hydrogen-hydrogen single bond that is 436. So the bonds broken are equal to all total are equal to 6 times 412 plus 348 plus 612 plus 436. So it takes 3,868 kilojoules per mole to break all of those bonds on that side. And hopefully I didn't miss any. Okay? And then we calculate how much energy is released. So now we're creating these new bonds here. there's 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. So now I'm going to go 8 times 412 plus, and it looks like we've just got 2 carbon-carbon bonds now, and they're single bonds, so that's 2 times 348. So 8 times 412 plus 2 times 348 equals 3,992. Okay, and again, this is how much energy it takes to break the bonds. This is how much energy is released when those new bonds are formed. So to get the total enthalpy change, this is our negative value, because that's the releasing part. This is our positive value. We're going to take 3868 and subtract 3992. 3868 minus 3992. So the enthalpy change for this reaction overall is negative 124 kilojoules per mole. Okay, I'm going to pause this video at this point, and I'm going to figure out what the answers to number 2 and number 3 are. I'm not going to show all the work, but I want you to pause it as well. When I come back, I'm gonna just quickly write down the answers for this. Okay, so this is what I got for number 2 and number 3. On number 2, my final answer, I could have made a mistake here. I got negative 45 kilojoules per mole all total for the enthalpy change for that reaction. I got 3675 for my reactants. Again, if you got something different, kind of look at how I drew it out. And then I got 3720 for my products. I took the reactants minus the products, and I got negative 45. On the number 3, be careful on number 3 because you've got 2 chlorines. Make sure you write both of those out so you remember to double that value for the chlorine-chlorine bond. It's real easy to just draw right, oh, well, Cl2, I'll just write that down once, and then you forget, and you only take 239. So it's got to be 2 times 239, same with fluorine, 2 times 154, same with the HF, and same with the HCl. Make sure you double both of those values. So for the reactants, I got 2434. For the products, I got 3632. I subtracted those and got negative 1198. And again, that's the enthalpy change for that reaction. Okay, and we're going to go ahead and stop there for today.